Okay, good evening, everybody. Let's begin. So in the last lecture, we were looking at the RKA methods, right? We were looking at the Runge-Kutta methods, and we said we're going to essentially, in which we have written y n plus 1 equals yn plus gamma 1 times k1 plus gamma 2 times k2. Right, this is what we have written, in which we said k1 is a function which is h times f of tn comma yn, and then k2 is also another function which is h times f of tn plus alpha h plus yn plus some beta times k1. Hello? Yeah. So that is what we have written. And then what we did was we expanded yn plus 1 using Taylor series, right? And then we have also hello.
Screen is not visible, sir.
Oh, screen is not visible.
No, it is visible, sir.
Yeah. Okay. Can I proceed?
Yes, sir.
Yes, sir. We can proceed, sir.
Okay. Thank you. So we have written yn plus 1 in terms of yn using Taylor series expansion, and also we have expanded what is k2 and then substituted for k2 and k1 in this equation, and then compared whatever the resulting equation with the Taylor series expression, right? And then we were able to compare these two, and then we got few conditions. Those conditions were, I think, gamma 1 plus gamma 2 equals 1, something like this, and then gamma 2 times alpha equals 1 by 2, and gamma 2 times beta equals 1 by 2. I suppose this is what we obtained in the last class. Let me just verify that. Can somebody tell me whether this is correct or not, whatever we got in the last class?
Yes, sir, correct.
Yeah, this is correct, or anything, did I miss something? We got gamma 1 plus gamma 2 equals 1, gamma 2 alpha equals 1 by 2, gamma 2 beta equals 1 by 2. Okay, so this is perfect. So what we got was we had 4 parameters, but we were able to only obtain 3 equations, right? So what we can do is that we can say that one of them is a free parameter. We can say alpha is a free parameter. Okay, that means we're going to set the value of alpha, and then we're going to then express the other values, beta, gamma 1, gamma 2, in terms of alpha. So the moment we change the value of alpha, all these 3 will change. Okay, then alpha is a free parameter, we can say. Then from these equations, what we get is, if alpha is a free parameter, gamma 2 equals 1 by 2 alpha. Okay, gamma 2 equals 1 by 2 alpha. Gamma 1 equals 1 minus 1 by 2 alpha. And then beta would be equal to alpha, right? Because gamma 2 alpha equals 1 by 2, gamma 2 to beta equals 1 by 2, in which case beta equals alpha. Okay, so these are the values we will obtain for gamma 1, gamma 2, and beta in terms of alpha. Okay, then now that we have obtained a scheme, I can go back and plug it in gamma 1, gamma 2. So we can substitute for what is gamma 1, what is gamma 2, what is beta in terms of alpha, right, into this equation. That means I can write this equation as yn plus 1 equals yn plus gamma 1, that is 1 minus 1 by 2 alpha times k1 plus gamma 2, that is 1 by 2 alpha times k2. Okay, and then k1 equals h times f of tn comma yn, and then k2 equals h times f of tn plus alpha h comma yn plus beta k1. Beta k1 is same as alpha k1. Okay, so that's what we have. So this is the this is now the RK2 method. This is called the second order accurate Runge-Kutta method. Okay, of course, I have not shown that this is actually second order accurate, which we're going to show in some time. Okay, this is a second order accurate Runge-Kutta method. Okay, so in general, the value of alpha in general is taken to be 1/2. Okay, so most of the times it is taken to be 1/2 in a general RK2 method. The most preferred value is 1/2. In which case, of course, the K1 coefficient is going to go to 0, gamma 1 will become 0, and then only gamma 2 will survive, that is equal to 1. Okay, so a value of, and then this is usually written in a slightly different form in the RK2 method. So what we do is that we take, for these values of gamma 1, gamma 2, and beta, first we're going to solve for K1. Okay, we're going to solve for K1. Then use the value of K1 and then solve for K2. Okay, and then solve for K2. Once we have obtained K1 and K2 from these equations, we're going to solve for yn plus 1. Okay, that means we are doing 1 and 2 function evaluations per calculation of one time step. That means when we want to go from yn to yn plus 1, instead of having one function evaluation, we are doing 2 function evaluations. Okay, but then you see that unlike the Taylor series method, where we were required to calculate derivatives of the functions, which was troublesome in certain cases, this is not required in the case of the RK2 method, right? Here we don't have to calculate any derivatives. Rather, the derivatives are replaced with the function values itself. So as a result, we just need to calculate what is the function value at a different time step location and at a different y location. Okay, so that means we have to calculate the same function value at this particular tn plus alpha h and yn plus alpha k1, and then once we have these 2 function evaluations, we can calculate yn plus 1. Okay, so that is the RK2 method, the Runge-Kutta second order accurate method. In general, the yn plus, these equations are written in a slightly different form in the RK2 method, and they are written in a method that is known as a predictor corrector form, in which it is written as yn plus half star equals h times f of tn comma yn. Okay, or it is I think h by 2 times f of tn comma yn, and then we calculate n plus 1, yn plus 1 equals yn plus half star plus h times f of tn plus 1/2 h comma yn plus half star. Okay, so typically they are written in terms of a predictor character form. So we first calculate what is yn plus 1 half star, and then we would calculate with that value. We will again evaluate this thing and calculate what is yn plus 1. Okay, so that is the RK2 method. Okay, any questions on this so far? Any questions, anybody?
Why are we writing this predictor?
Sorry?
Why are we writing this predictor character form?
Why am I writing?
This predictor character form we wrote last time, so there's 2 equations. Why are we, what is the...
No, in general, it is basically the same. So if you plug in alpha equals 1/2 into this equation, it is going to give you the same equations as I have written here. Okay, so there is no difference in those terms. It's just that it is preferred to write it this way. So it is exactly the same equation as before. Okay, but people kind of write it in this way, where you predict the value of yn plus 1 half star, and then using the predictor value, it is corrected to yn plus 1. So that is how it is interpreted in a different way. But the equations are exactly the same between between this one, if you substitute alpha equals 1 by 2 and this one, okay, they are exactly the same. There is no difference as such. Okay, so I'm anyway going to go back and work with this one for different values of alpha a little later. Okay, so that is the second order accurate RK2 method. Now let us look at the stability and accuracy of RK2 method by using the linear analysis that we have introduced before. Okay, so let us look at the linear analysis and then see what are the stability properties of the RK2 method and what is the accuracy, right? We have said this is second order accurate, and then we will also look at its behavior for purely imaginary values of the right hand side, okay, for purely imaginary lambda and so on. So what is the model problem? The model problem that we want to solve is y prime equals lambda y. Okay, that is the model problem we want to solve. And then what we obtained is, we obtained yn plus 1 equals yn plus 1 minus 1 by 2 alpha k1, all these things. So let me repeat this thing. Okay, so essentially we want to now solve this model problem using RK2 method, which is basically given by yn plus 1 equals yn plus 1 minus 1 by 2 alpha times k1 plus 1 by 2 alpha times k2. Okay, note that I'm not using the value of alpha equals 1 by 2 here. I'm deriving it for in general for an RK2 method, not specifically for alpha equals 1 by 2. Okay, and then we said k1 equals h times f of tn comma yn, and then k2 equals h times f of tn plus alpha alpha h alpha h comma yn plus, or is going to be yn plus alpha k1. Okay, that is what we have. Okay, so now I have to put in I want to now solve it for this particular model problem. So if that is the case, for the model problem I have, my k1 is going to be h times, what is f of t and yn? F of t and yn is my lambda y. The right hand side, f of t and yn is only a function of y in this case. There is no dependency on t. So as a result, I can write this as essentially f of t and yn is nothing but lambda times yn. Okay, that means lambda h yn. Okay, that is k1. Similarly, I can write what is k2. K2 equals h times, what is f of tn plus alpha h times yn plus alpha k1. So that is nothing but again lambda y, that is the function, but then lambda, but y is now yn plus alpha k1. So it means this is going to be yn plus alpha, but k1 is again nothing but lambda hyn. So this is going to be lambda hyn. Okay, so that is my k2. That means this is equal to lambda hyn plus alpha times lambda square h square yn. Okay, that means my k2 is equal to lambda hyn times 1 plus alpha lambda h, right? That's going to be lambda h, right? This is lambda h. This is lambda hyn times 1 plus alpha lambda hyn. Okay, so that is my k2. So if I'm going to substitute for k1 and k2 back into this yn plus 1 equation, what I get is yn plus 1 equals yn plus 1 minus 1 by 2 alpha times k1, that is lambda hyn plus 1 by 2 alpha times, okay, I can even leave it as it is. Okay, so lambda hyn plus alpha times lambda square h square yn. Okay, so if this is the case, let me try to simplify this thing. So I'm applying RK2 method to this model problem. Model problem is y prime equals lambda y. So what we get is, we get 1 yn plus, when you multiply with these two things, you get lambda hyn, and you get minus 1 by 2 alpha lambda hyn plus 1 by 2 alpha lambda hyn, plus we have alpha gets cancelled and you get lambda square h square by 2 yn. Okay, and then here we see that we have a minus 1 by 2 alpha h lambda hyn plus 1 by 2 alpha lambda hyn. So this gets cancelled. So we end up with yn plus lambda hyn plus lambda square h square by 2 yn. Okay, that is my yn plus 1. That means my yn plus 1 equals 1 plus lambda h plus lambda square h square by 2 factorial times yn. Okay, now we got this value, which is sigma. Okay, so we can write any yn equals sigma power n times y0. That is the amplification factor we have. Now, by observing the this quantity, that is 1 plus lambda h plus lambda square h square by 2, with the exact solution. Exact solution was e to the power lambda h, right? We said e to the power lambda h is 1 plus lambda h plus lambda square h square by 2 factorial plus lambda cube h cube by 3 factorial. Lambda cube h cube by 3 factorial and so on. Right now we can see that it is matching up to the second term, right, or the third term, the second order accurate term, 1 plus lambda h plus lambda square h square by 2 factorial. As we said, if a particular series, this particular series is, if it is matching up to lambda power alpha, h power alpha by alpha factorial, then we say that that method is alpha order accurate. So as a result, because it is matching up to second order, we say that this is a globally, so RK2 is globally second order accurate. Okay, it's globally second order accurate. Fine. So we have established the order of accuracy of the RK2 method. Then let us look at stability, right? Stability. Okay, so what do we do for stability? Stability is basically, we know that if the modulus of sigma is less than or equal to 1, then we can call that method as being stable. Okay, that means we want 1 plus lambda h plus lambda square h square by 2 factorial, modulus of that to be less than or equal to 1. Okay, but we know that in general lambda can be a complex number, right? That means lambda can be equal to lambda real plus I times lambda I. Okay, but then here, unlike before, in the case of, if you recall, in the case of explicit Euler, we got an equation for, so when we have substituted for lambda, we got an equation of a circle that is centered at -1, 0 and has a radius equal to 1, right? So we were able to draw the stability diagram for the explicit Euler. We said explicit Euler, it is a circle something like this. It's a circle, right? And then we said this is -2, this is -1, this is 0. So this is the region of stability for explicit Euler, right? Where we wrote this is the real part of the lambda h, and this is the imaginary part of the lambda h. Okay, so that's what we have written, but we were able to comment on that because the equation was popular, familiar to us. We were able to correctly recognize it. Now this is not an equation that is so straightforward, right? Because it has 1 plus lambda h and lambda square h square by 2, and we want the modulus of that to be less than or equal to 1. So now we want to know what kind of diagram is this thing. Of course, it is only conditionally stable, but we want to know the diagram, right? So we want to now calculate the region of stability. Okay, for this case, that is 1 plus lambda h plus lambda square h square by 2 modulus to be less than or equal to 1. Okay, so one way to go about this is to equate 1 plus lambda h plus lambda square h square by 2 to be equal to 1 times e to the power I theta. Okay, because it is 1, we want to draw the stability region, stability diagram. So, and then we vary the value of theta. Let us say 0 to theta less than 2 pi, or we can even only vary till pi because it will be symmetric for up and down. We can vary from 0 to pi, and then solve this equation, essentially obtain the roots of the above equation for different values of theta, right? That means once I know the theta value, I know the right hand side is basically going to be cosine theta plus I sine theta. Then I can solve for this equation with this right hand side, and then solve for the roots of this equation. That is going to give me what is the value of lambda h, which will lie on that curve, right? Whatever is the curve. But then again, we realize that lambda h is in general, lambda is complex. So this is lambda r plus I lambda I. That means we need a, so the root finding routine, we want it to be able to handle complex polynomials. Okay, that's what we want to know. Then otherwise, what you can do is you can perhaps equate the real part of this thing and the imaginary part of this thing to cosine theta and sine theta respectively, and then obtain the value of lambda r h and lambda I h for each and every theta, and then you have to plot all these things. Okay. So if you have to equate the real and imaginary part separately and then do it, then that means you're actually doing a solution of system of nonlinear equations, right? For example, we can perhaps look at this thing. That means either you have a complex root finding method, for example, the Newton-Raphson method or bisection method. You can try to implement it for a complex number, or we can actually look at a simple root finding method which works with simple real numbers, and then convert this thing into two, right? For example, I can write this as 1 plus lambda r h plus I lambda I h plus I have lambda r plus I lambda I square times h square by 2, okay, which is going to give me 1 plus lambda r h plus I lambda I h plus lambda r square h square by 2 minus lambda I square h square by 2, and then we get plus 2 lambda r lambda I, which will, where the 2 in the denominator will cancel it, you get I lambda r lambda I h square. Okay, that's what I get. That means I'm going to write this as two equations. One equation is where all the real components are there, with is 1 plus lambda r h plus lambda r square h square minus lambda I square h square by 2, right? That is my real part. Plus I have the imaginary part, which is lambda I h plus lambda r h times lambda I h. Okay, so we will equate this to cosine theta plus I sine theta. Okay, that means we have two equations and two unknowns. That means I can write this as two real equations, 1 plus lambda r h plus lambda r square h square by 2 minus lambda I square h square by 2 equals cos theta. And then we have lambda I h plus lambda r h into lambda I h equals sine theta. Okay, so essentially we solve for system of nonlinear equations. Right, and then obtain a root for this, right? Using some initial guess value for the root, we will obtain a root. Okay, either we do it this way or we directly use a complex root finding algorithm, right? Then we can go and then see what will be that curve. That means you will obtain for one value of theta, you're going to get what is going to be lambda r h and lambda I h. Then you would mark that point. Similarly, you will take another value of theta and then you will obtain this value and you will mark that point and so on, right? So you're going to mark all those points. Then you're going to get basically, if you connect all those points, you're going to get the stability curve or stability region, right? Whatever is that is inside that curve is going to be the stable region, and everything that is outside that is unstable region. Okay, so if you do this exercise, what you're going to see is that you're going to see that. Okay, so that's my real axis. So this is real of lambda h. This is imaginary of lambda h. Okay, and then this is -1. This is -2. Earlier we had this circle. I don't know if I can draw this. Okay, so we have this circle. Yeah, so this is for the explicit Euler, right? So this is -1. Oops. This is -1. This is -1. This is -2. This is 0, and the circle is only a tangent. So we said this is for the explicit Euler. So this is for the explicit Euler. Now, if you go do this exercise, whatever I have just described, you're going to get a diagram that looks like something like this. Okay, it's going to be something like this, a little bit elongated. Okay, you can do it. Yeah, it will be something like this. It'll essentially be exactly like what we had for the circle. Okay, so it will have the same stability region where for purely real value of lambda, that is, it's going to end at -2, but this quantity, okay, I think it will be a little more rounded as such. Okay, this quantity is about square root 3, so this will be about minus square root 3. So that is the stability region. So everything inside is stable. Okay, that is for RK2 method, and everything outside is unstable. Okay, that means I have calculated what is lambda h for each and every theta. Okay, so once I calculate this for each and every theta, that is what I have obtained as my curve. Okay, so that is what I have obtained. Okay. So what do we see? What we see is that the RK2 is has a much larger stability region than explicit Euler. Although for real numbers, the explicit Euler and RK2 have pretty much the same stability region. That is this much only. Whereas for other complex numbers, we see that RK2 is much more stable because it has this region, which is it has this much coverage, right? So this is the entire region where it is stable, right, for RK2, right, which was not the case for explicit Euler. So we see that the for RK2, the region of stability is much bigger, or is bigger. Let me say just bigger, not much bigger. Okay, so just bigger or larger than explicit Euler in general for complex lambda. Okay, that means we are not talking about just purely real lambda, because for purely real lambda, it has the same extent as the explicit Euler. But then we also see that still the stability diagram is still a tangent to the y-axis. That means we cannot have purely imaginary lambda and then obtain a solution with RK2, right? Because it shows that we are going to lie outside the stability region. As a result, RK2 will not converge to purely oscillatory problems where there are only lambda I and lambda r equal to 0. Okay, that means for purely imaginary lambda, RK2 is unstable. Okay, or unconditionally unstable. We can say that this is unconditionally unstable. Okay, just like the explicit Euler method. Now we should be able to prove that also from the equation. So the equation we got was essentially 1 plus lambda h plus lambda square h square by 2, right? That is my sigma value. Okay, so we want this magnitude modulus of this to be less than or equal to 1 for to obtain a stable method. But then if I have purely imaginary lambda, then my y prime equals I omega y, in which case lambda are equal to 0 and then lambda I equals I omega, right? In which case I'm going to substitute here for this value, which is going to be 1 plus I omega h plus I square omega square h square by 2, right? That is going to be my sigma, which is going to be 1 plus I omega h minus omega square h square by 2. Okay, so that is my sigma. Then if I were to take what is the modulus of sigma, that is going to be square root of the real part, that is 1 minus omega square h square by 2 square, plus the imaginary part, that is omega square h square. Okay. Yeah. So that's what I have. That means if I were to calculate what is this value, this is going to be square root of, this is 1 plus omega power 4 h power 4 by 4 minus 2 times 1 time omega square h square by 2 plus we have omega square h square from here. Okay. So that is essentially going to be 1 plus, so we have minus 2 times omega square h square. This basically gets cancelled. So what we have is 1 plus omega power 4 h power 4 by 1 by 2 to the power by 4 to the power 1 by 2. What is this value? For all omega values, right? This is going to be positive, right? So this is always positive. So it means this is always, sigma is always greater than 1, right? In fact, not equal to even 1. This is always always greater than 1. That means RK2 is unconditionally unstable for purely imaginary values of lambda. Okay, that means we cannot solve it for purely oscillatory problems. It is still unstable. Okay, so that is what we kind of obtain from here. Okay, any questions so far, anybody?
Sir, I have one doubt.
Yeah.
Sir, can you please explain why you chose, while equating sigma to e power I theta, the amplitude as 1?
The amplitude as 1?
Yes, sir.
Yeah, no, essentially what we want to see is that we want to look at mod sigma equal to 1 region, right? Because that is going to define whether it is going to be, so this is the marginally stable region, right? For example, if you take this circle, everywhere on this circle, value of sigma will be equal to 1, right? So anything inside this, the value will be less than 1. Anything outside, the value will be greater than 1, right? Think of it like a quantity, right? So earlier we had, what was the expression for explicit Euler? Even if you take for this one, we have 1 plus lambda h plus lambda square h square by 2, right? Now, wherever this quantity is equal to 1 in magnitude, that is the stability region, because this is my sigma, right? If it is mod sigma equals 1, that is the stability curve. Anything more than that is going to be outside this curve. Anything less than this thing is going to be inside the curve, right? So that's why I've taken it to be 1. But then we can also take the phase, which is e to the power I theta, right? Theta is going to give me how much the lambda IH and lambda RH are related, right? That's why I have taken it to be 1. Is it clear?
Yes, sir.
Yeah, okay. Any other questions, anybody?
Sir, can you go down to purely oscillatory problems? Sir?
Yeah, oscillatory, yeah.
Yes, sir. So here, square of I omega h will be minus omega squared h square, right?
Yeah, so this is the real part. So real part is this one, and then this is the imaginary part. So we have, if we have a plus ib, magnitude of a plus ib is square root of a square plus b square. Okay, so 1 plus I omega h, so 1 minus omega square h square is the real part, plus I omega h. I omega h is going to be simply omega square h square, right? This is like ib, right? The
Yes,
magnitude,
sir, but,
yeah.
I squared will become -1, right? There.
Yeah, here I square will become -1, but then this is, you will not consider I square here, right? Because this is the imaginary part. So magnitude of a plus ib is square root of a square plus b square.
Understood, sir.
Yeah, yeah. Okay, anything else? Anyone else? Okay, if that is the case, now let us look at the phase errors. So we have been looking at the amplitude errors till now. What about the phase errors? Okay, so what did we do? So essentially we said to calculate the phase errors, we will again look at purely oscillatory problems. That's what we said. Okay, so I can go back to this equation, that is sigma equals 1 plus omega h minus omega square h square by 2. Okay, so what we have is we're trying to solve y prime equals I omega y, and then sigma is what we get as 1 minus omega square h square by 2, 1 minus omega square h square by 2 plus I times omega h, right? I times omega h. So that is my sigma. That is my sigma. So this is nothing but essentially the magnitude, which is sum a times e to the power I theta, right? So a we already know. A is basically square root of this thing, which we already saw, right? 1 plus omega power h power 4 by 4. Okay. Now we may ask, like, why is it is always unstable? Why are we looking at phase errors? But then we are still looking at phase errors because even if there are other complex lambda for which lambda r is not equal to 0, that means it is not purely oscillatory, then also we can solve for this, right? So that is the reason I'm looking at this particular phase error. So that is going to be, so this theta would be what? Theta would be tan inverse of complex, the imaginary part divided by the real part. That means omega h by omega square h square by 2, okay? But we know that this is theta for RK2, right? But then what is theta for exact solution? Exact solution theta was equal to omega h, right? This we have established before, because your y equals y naught e to the power omega t, which is equal to y naught e to the power omega h times m, okay? So the phase is given by omega h for each time step. So it is the exact. But then we want to know the phase error. That means we want to calculate what is theta exact minus theta RK2, okay? But before I can use this, I need to make this theta RK2 a little bit better. So theta RK2 equals tan inverse of omega h by 1 minus omega square h square by 2. But we know that tan inverse x equals x minus x cubed by 3 plus x power 5 by 5 and so on, okay? That is going to give me tan inverse of this is nothing but omega h by 1 minus omega square h square by 2 plus omega h by 1 minus omega square h square by 2 cube. Sorry, this is with a minus. And then plus 5 everything, okay? But then in each of these things, I can use again another formula, which was for 1 by 1 minus x. We know that this is equal to 1 plus x square and so on. So that means wherever we are getting this quantity, 1 by 1 minus omega square h square by 2, 1 by 1 minus omega square h square by 2 with multiplication with omega h and all. So I'm going to write as 1 plus omega square h square by 2, that is my x, plus x square, that is omega power 4 h power 4 by 2 square, that is 4, and so on, okay? Which I'm going to substitute for in each of these expressions here, okay? That is going to give me this as omega h times 1 plus omega square h square by 2 plus omega power 4 h power 4 by 4, and so on. And then I'm going to get minus omega cube h cube times, again the same thing, 1 plus omega square h square by 2 plus omega power 4 h power 4 by 4 and so on cube, okay? That's what I'm going to get. So essentially, what does this mean? This is going to be omega h, and then divided by 3, right? Divided by 3 was also there, right? So this is x minus x cubed by 3. So there is a 1 by 3 here, okay? Plus 1 by 5 and so on. So there is a 3 here, okay? So this is going to be omega h plus, if I multiply with this, you're going to get omega cube h cubed by 2 plus omega power 5 h power 4 by 5 and so on. And then here we get minus omega cube h cubed by 3 minus omega power h power 5 by 6 minus something, okay? So this is going to be omega h plus omega cube h cubed by 2 minus omega cube h cubed by 3. That is going to be omega cube h cubed by 6, right? And then you're going to get plus some order h power 5. So that is the phase for the RK2 method. Okay, that is the phase for the RK2 method. Okay, then what is the phase error? That is theta exact minus theta for RK2, that is going to be omega h minus, this is omega h plus omega cube h cube by 6, and so on. So that is going to be omega h gets cancelled here. What we obtain is we get minus omega cube h cube by 6. Okay, now we see a couple of things here. This is actually has a minus in the front, unlike previous calculations. The explicit Euler was omega cube h cube by 3 with a plus, right? But this is a minus, and then this is also it can be written as essentially minus 1 by 2 times omega cube h cube by 3. Okay, so omega cube h cube by 3 was the phase error for explicit Euler. So this was for the explicit Euler. So we see that the phase error for RK2 is actually 1/2 the phase error for explicit Euler. So that means the phase error is smaller, so it's going to be not so much deviant as compared to explicit Euler. It is going to be only half of that. But then we see that there is a minus here rather than a plus. That means earlier we said that explicit Euler as well as implicit Euler and trapezoidal method, these three methods, they had some omega cube h cube by some factor, okay? But then they always had a plus value, where we said that these were all, they had a phase lag, right? So when we had a positive value for the phase error, we said these methods are phase lag methods, whereas when you say phase error is negative, then we say that this particular method is a phase, has a phase lead, okay? What is phase lag and phase lead? We have already seen that. So phase lag we have observed for explicit Euler, implicit Euler, and then trapezoidal. Okay. Whereas now we say that this particular RK2 has a phase lead. Okay. So what does it mean? So earlier we have seen in that context, if my exact solution was something like that, okay, we obtained a solution with let us say trapezoidal or something which was neutrally stable, right? Neutrally stable. It was neither growing nor decaying, but there was some phase shift, right? So I'm going to a little bit exaggerate and show the phase shift, although it is not going to be so much phase shift in the initial time period. Okay, so that is the time period. This is the solution. So I kind of show this thing. So there is some phase shift. This is what we called as phase lag, right? This is for trapezoidal. Okay, but then why are we calling it as phase lag? This is actually coming. It is actually before the wave rather than after the wave, but still we are calling it as phase lag. Lag means something that is coming later. So similarly, if you look at, let us say, the RK2 method, it is actually unstable, so it's going to diverge, but then it's going to follow this one. Okay, it's going to be like this, RK2. So the green is RK2, which we are calling it as phase lead. Okay, but then why are we calling it as phase lead? This is the blue one is the exact solution, right? The blue one is the exact solution. And we call the trapezoidal as a phase lagged, and then RK2 is phase lead. Are we wrong in saying that, or what is the idea here? Can someone explain what this means, or is this correct or is it incorrect? This is some amplitude. Let us say this is Y. Okay, so what we mean here is that when we say phase lag, we know that, so this peak, let us say if you look at the peak, this peak has come at some time t1, okay? Whereas this peak now will come at t2, which is greater than t1, right? T2 is greater than t1. That means it is arriving at a later time. That is why it is called phase lagged, right? You're going to see the peak later, okay? Similarly, at a much later time. Similarly, if you look at RK2, you're going to see the peak, let us say T0. T0 is less than T1. That means you're going to see the lead, the peak before ideally it should appear, right? That is why this is phase lead. You're going to see it much more quickly than at the time where it is supposed to appear. That's why it is called phase lead, okay? So that means whenever you have negative value for phase error, it is a phase lead, and then whenever you have a positive value for phase error, it is phase lag. Okay, so I think it's nice to keep in mind about the phase lead and phase lag in this context. Okay, fine. Any questions so far? So that finishes basically the RK2. Now I'm going to talk about the Runge-Kutta method, the fourth order accurate method, that is RK4. That is the fourth order accurate Runge-Kutta method. Okay, so the fourth order accurate Runge-Kutta method is the most used, okay, or popular method for solving first order initial value problems. Okay, so this is most widely used method, RK4 method. You must have used in your work several times. So before we go into this thing, it's going to be quick, but then any questions so far?
So it's clear, sir. Can
Clear? Okay, fine. So let's look at the RK4 method. This is the most popular, widely used method, which is the RK4 method. Okay, so this is, as the name suggests, this is globally fourth order accurate. Okay, this is globally fourth order accurate, and then it is given as follows. So it is essentially yn plus 1 equals yn plus 1 by 6 of k1 plus 1 by 3 of k2 plus k3 plus 1 by 6 of k4. Okay, so that is the value, and then k1 equals h times f of tn comma yn, and then k2 equals h times f of, or h by 2 times f of tn h by 2 times, I suppose, f of tn plus 1/2, and then k1 plus this is going to be, it's going to be k1. Okay, it's going to be at p1 plus k1. Okay, and then k3 is going to be h by 2 times f of tn plus not 1/2, actually I should say tn plus h by 2, right? Tn plus h by 2 comma k1. Okay, and then this is going to be tn plus h by 2 comma k2, and then k4 is going to be h times f of tn plus h comma k3. Okay, so that is the RK4 method, which is the most popular. Okay, most widely used method. Let me just check my coefficients if it is correct or not. So what I have is h by 2. Oh, sorry, I should write y1 plus k1 by 2, y2 plus k2 by 2. Okay, so this is not just k1, so this is y1 plus. Okay, so this is y1 plus k1 by 2. It's going to be y1 plus k2 by 2, and then this is y1 plus k3. Okay, that is y1 plus k3, and this is tn plus h by 2, tn plus h by 2. There is no h by 2 in the front. Okay, so these are just h. Okay, so that is what I have. Okay, so that is the RK4 method. I will anyway give you these values in the exam or in the analysis, in the assignments and all, so you don't have to remember these values. Okay, so
Sir?
Yeah.
Sir, it should be yn, right, sir?
Oh, sorry, not y1, yn. Yeah, these are yn plus yn. Yeah, correct. Thank you. Yn, so tn h by 2, and then yn plus k1, k2, k3 by 2. So what you do is that you start from tn yn. You're going to calculate what is k1, then use that k1, and then h by 2, and then calculate k2, then calculate k3 using the k2 values. Then once you have k3, you're going to calculate k4. Then once you have k1, k2, k3, k4, you're going to go back here and calculate yn plus 1. So as you can see, there are 4 function evaluations. Okay, there are 4 function evaluations. So it is actually fourth order accurate globally. Now you see, if we were to do this thing with Taylor series approximation, we would have to calculate the fourth derivative for y and then replace it with, f and so on. So which we are not doing. So RK4 is, is avoids all that problems, right? Because of because it introduces several points between Tn and Tn plus 1. Okay. Now, if you want to apply the model problem, that is y prime equals lambda y, right? And then write k1, k2, k3, k4, and then substitute into yn plus 1, just like the way we have done it for the RK2. Then what you're going to see is that we're going to see sigma equals 1 plus lambda h plus lambda square h square by 2 plus lambda cube h cube by 3 factorial, that is 6, plus lambda power 4 h power 4 by 24. Okay, so this is what you're going to see for sigma. If you substitute for lambda y into each of these things and then collate everything into this and then write it as yn plus 1 equals some sigma times yn. Okay, then that is the sigma you're going to get. Fine. So that means this is now going to determine the stability properties. So again, if I want to obtain the stability region, right, then what should I do? I basically would equate this sigma value equal to some 1 times e to the power I theta. I'm going to vary my theta from 0 to pi and then going to calculate the stability region. So if I do all this, again using a complex root finding polynomial or root finding method, or if I use a system of nonlinear equations or something, in which case I'm going to get the stability region. Stability region will look something like this. So I'm directly drawing it here. So okay, so what we have is we have the real part of lambda h and then the imaginary part of lambda h. Then what we have is the stability region. So stability region will go, let's say this is -1, -2, -3. Okay, so it'll go almost up to -3, about 2.78 or 8 or something. And then it'll go almost up to 3. It will go to almost 2.8. Here it'll go almost up to -2.8, that is 3. Okay, that is the value of 3. So what you're going to see is that it is going to look like it's going to look something like that. Okay, maybe it will be a little bit better. Okay, so it's going to look like that. So that is the sigma equals 1 graph. That means everything inside is stable, everything outside is unstable. What you see is that now this is a significant improvement over our previous methods. The previous methods were, the RK2 was something like this. It was going to almost to square root 3. Oops. Okay, it was going to almost to square root 3, something like this. And then the explicit Euler was even smaller, right? Explicit Euler was basically a circle, right? Okay, so what you see here is that the stability region has improved, right? And we also see that even for purely, let us say for lambda r, even for purely oscillatory solutions, you will still get a stable answer, right? Because the stability region includes that. So purely oscillatory problems also, it is going to give you stable solution, right? But then what you see is that even for lambda r greater than 0, which is on to the right hand side of this thing, you're going to get stable solution, right? This is actually not correct, because ideally, theoretically, lambda r greater than 0 is actually unstable, right? Because it is positive, it should actually diverge. But RK4, because of its stability properties, it's going to give you artificially stable solution. Okay, which is not correct, but probably it can be used in some instances where if it is required. But then otherwise, we see that there is a large area all around which has improved the stability properties. Okay, so that is about the RK4 method. Fine. So we're not going to do the phase error and other things for RK4. It's kind of quite involved, but we're going to, with these observations, we're going to kind of stop here. After this, we will look at the solution to system of ODEs. Okay, that we will do in the next lecture. Okay, so in the next lecture, we're going to look at solution to system of ODEs and then how to solve the boundary value problems. Okay, so these two are what we're going to see next. Okay, so I'm going to stop here. If you have any questions, you can ask me. Any questions, anybody?
Sir, regarding the midsem exam, as we discussed earlier, we will go with closed books exam.
Yeah, we'll go with we will go with the closed book. Yes.
And a formula sheet for two pages.
Yes. We'll go with closed book exam and then formula sheet. Yes.
Okay.
Yes.
That code office will allow us to take the formula sheet, no, sir?
Yeah. I'll inform them. That should be fine.
Okay, sir.
I'll inform them today. But then regarding this final exam, change of date, I talked to code office. I mentioned to them, they said, they have made, they are making all arrangements for the exam to be on the scheduled day, with help with the whoever is the, conducting the exam. So as a result, it is not possible to change the date is what they're saying. So what I would suggest is maybe you prepare as if the exam is, going to be 1 week before and be ready. I think, that is going to be the scenario right now.
Okay.
They said unfortunately they cannot move it because there are other logistics which they are planning for exam center and other things. So that is the reason. Yeah. I think it will be back to back, but I think that is okay.
Is it possible to your exam is on 21st, sir? 21st.
21st, okay.
Yeah. It is second half. Is it possible, sir? At least.
I don't think so. They said they have already made, arrangements, everything with the management, I think it will be according to whatever is the calendar is there,
Right, sir.
Yeah. But I think I would suggest you can prepare, earlier ahead itself so that, you don't have to, don't prepare on the day before or something. Even prepare as if it is on, 15th or 16th and be ready. And then 1 day before you can do the revision or something.
Right, sir.
That is all I think we can do as of now, because I think there seems to be a lot of logistics and some some other, third party company which is involved in conducting all these exams and other things. That's the thing. Yeah.
Sir, regarding the question paper, what yesterday you are given for the
practice problems. Yes.
So, whether we can get it today, sir, because we have to work it.
Yeah. They have not yet posted, is it?
Yeah. I checked with the code office. They said it is not received from.
No, practice problems, no?
Yeah, practice problems.
I have given them, I have sent them. I'll anyway check with them again. I gave them. Otherwise, I can send as an attachment to all of you, right? In the mail also.
Yes, sir. Yes, that will be better, sir.
Sure. I'll just send it as an email. I'll also, remind them that it should be uploaded. I have sent them yesterday together with the programs also I have given. I don't know why they have not uploaded them yet. I'll check them. Yeah, I'll check with them today itself. Okay.
Okay. Sir.
Yeah. If you have any questions from now to exam, please feel free to write to me or to the TAs. Okay. Otherwise, good luck with the exam. Exam is on Sunday, is it? 16th?
Yes, sir. 16th.
Okay. Good luck with the exam. I think you should be able to do fine, once you prepare for all these problems. Okay.
Sure, sir.
Yeah. Okay.
Thank
Thank
you.
you, guys.
Thank you so much, sir.
Thank you, guys. Thank you very much. See you on Monday, 17th.
Thank you, sir.
Thank you. Bye. Yeah.
Thank you so much, sir.
Thank you very much. Yeah. Bye.